Taken 1 year before Neil Armstrong and Buzz Aldrin landed on the moon. Christmas 1968. NASA astronaut Bill Anders photographed the rising Earth. The Apollo 8 mission was supposed to explore the surface of the moon. But instead, the astronauts discovered the blue planet. The Earthrise photograph became an icon and a symbol for environmental protection. Since then, we have learned a lot about the delicate balance of the Earth system and the dangers that threaten it. Today, space travel is a key driver for understanding and protecting this unique celestial body. It feels the pulse of the planet. Since the Apollo 8 mission in 1968, Earth's population has more than doubled. But knowledge about the planet has also grown. Global cooperation has strengthened space travel. Today, it makes an indispensable contribution to the protection of the Earth and gives us a unique perspective. Looking from space, it becomes clear that the only habitable planet in our solar system is the result of numerous coincidences, and as such, an invaluable stroke of luck. Thousands of satellites orbit the Earth. The observers in orbit do not leave the planet's side and provide us with a comprehensive picture of its condition.
Earth observation has actually developed as an outstanding technology for observing the Earth in its entirety without any gaps. If we have learned anything from the last 20, 30, 40 years, it is ultimately that everything is interconnected, and that for every action, there is an equal and opposite reaction. And in this respect, you need to think systematically. Earth observation provides us with the opportunity to document planet Earth and its spheres, that is, the atmosphere, the oceans, the land surfaces, in their development, without any gaps and over entire areas. This is something no other technology can do.
Using highly specialized instruments, satellites can also detect processes that are not visible to the naked eye, such as gas compositions. NASA's Orbiting Carbon Observatory 2, or OCO2 for short, and its successor OCO3, which is attached to the International Space Station, specialize in carbon dioxide. Strictly speaking, the instruments do not measure CO2 directly, but rather its influence on solar radiation.
The source of light, so to speak, is the sun. We are very familiar with the spectrum of the sun, and the sun now irradiates the Earth, and there are various substances and gases in the atmosphere that absorb or reflect the radiation of the sun in certain wavelength ranges. And the instruments look very closely into these wavelength ranges, which we know for the different trace gases.
OCO3 can recognize about 17,500 different colors. Each gas reflects a specific mixture of the color spectrum, so each measurement is like a fingerprint. Other missions, such as ESA's Sentinel-5P satellite, also measure methane, nitrogen oxide, or ozone in the atmosphere. If the different data sets are combined with one another, we can get an even better picture of what's going on. For example, we learn about how much CO2 comes from the Earth's natural carbon cycle and how much we produce as people. Because fossil fuels also produce nitrogen oxide, a combination of CO2 and nitrogen oxides points to human emissions. And these have been rising ever since the beginning of industrialization, heating up the atmosphere.
Our ability to share data from space at all times, from the ISS, for example, and what we humans have learned from it, the astronauts' view, so to speak. We can access this at any time and see what they see. The astronauts have reported that we can already see coral bleaching globally due to the warming of the oceans. They've shown how the drought spreads, how brown Europe can become when there's a lack of water, a lack of rain, and when it gets too hot. And this view of the Earth from the outside as a whole is essential for all of us to understand that, yes, there's only one Earth, and the skin of the Earth is changing fundamentally, and not for the better.
Space exploration led to the discovery of the blue planet and the realization that the Earth is an anomaly within our cosmic neighborhood, a life-giving oasis in the midst of darkness. But this oasis is in danger. Its natural cycles are out of balance. To protect the Earth, humankind needs to venture into space. All you have to do to see how habitable our planet actually is take a look around the cosmic neighborhood. Our solar system is just one of many in a galaxy of which there are countless ones in the infinite vastness of the universe. It's thanks to a series of lucky coincidences that the Earth is habitable for us at all.
The Earth is extremely special because of its astronomical position, its distance from the Sun, the axis on which it spins, its seasons, water, and the atmosphere that made the development of life possible. And that is why it is important that we preserve the systems as they are, so that life can continue to thrive in the long term.
The most important factor for life is the Sun. With a surface temperature of 6,000 degrees Celsius, the Sun is the basis of all existence.
What makes it special is that it's close to us. It's the center of the solar system. And although it's 150 million kilometers away from us, it's close enough that its light, the energy it emits, is enough to keep the Earth warm.
This makes life possible. It's the heart of our solar system, provides energy, and determines the constellation of the planets. The Earth lies in the so-called habitable zone, close enough to the warming star for liquid water, and far enough away for that water not to evaporate. Compared to other stars, the Sun is medium-sized, and its activity is relatively stable. But even inside our star, with its 15 million degree hot core, nuclear fusion reactions are constantly taking place. In this process, charged particles escape from the solar atmosphere into space and flood the entire solar system. This solar wind, which also reaches the Earth, encounters its magnetic field, a protective shield against influences from outer space. The charged solar particles move along the magnetic field and react with the atmosphere at the poles. Auroras appear, and solar wind becomes visible.
From time to time, eruptions occur on the surface of the Sun. During such eruptions, a part of the Sun's atmosphere is essentially expelled at speeds of up to 2,000 kilometers per second. And then there's this huge cloud of charged gas particles, which is millions of degrees hot, a magnetic field flying through space at huge speed. Fortunately, most of these mass ejections from the Sun, as they're called, fly harmlessly past the Earth.
But sometimes, such solar storms also hit the Earth and can have a massive impact, damaging satellites.
This can lead to interference in communication. If you find that you suddenly have bad reception in an area where it's usually good, it could be your operator, and in all likelihood that'll be the case. But it could also be the Sun.
In extreme cases, data can be deleted or power grids can fail. At the same time, the demand for sensitive electronics continues to rise.
What we're essentially doing is exposing ourselves as a civilization to the changing moods of the sun, if you will.
The Earth's magnetic field, which protects us so well from the whims of the sun, is created by movements in the Earth's core. Earth is a rocky planet with a solid surface, but at its core, it's seething. The outer core of the Earth can reach temperatures of up to 5,000 degrees Celsius. This liquid layer of iron and nickel generates the so-called geodynamo, thanks to the Earth's rotation, and hence the magnetic field. The fate of our neighboring planet Mars shows what can happen to a planet without such a strong magnetic field.
We've only found few places on Mars where there's a magnetic field, and for the most part, its magnetic field is very weak. This means that Mars's atmosphere is less able to protect itself against the solar winds that hit the planet, and this lack of a strong magnetic field has already resulted in certain particles being torn out of the atmosphere by solar winds, which are then carried off elsewhere. And there's evidence to suggest that not only was there more water on Mars, but that at least some of this water was carried off by solar winds.
The Earth's magnetic field protects our atmosphere, but it does not help to protect us against all of space's dangers. After all, meteorite impacts can have catastrophic effects. But the Earth has a bodyguard. Jupiter, the largest planet in our solar system, can deflect celestial bodies with its great gravitational pull, which may otherwise hit the Earth. Before Jupiter reached its current position in our solar system, the Earth's surface was frequently hit by meteorites, and evidence of this can still be seen on the surface of the Moon. The Moon isn't alone in this either, as the Earth also bears some scars of times past. Our Moon itself was probably formed by a meteorite impact on Earth, another stroke of luck. Earth's gravity keeps the Moon in its orbit, and despite its own low gravitational pull, the Moon aligns itself with the Earth's axis and provides stable climatic zones and a consistent length of day. Earth's gravity, it's not just the thing that binds the Moon to us, but it also provides for a thin layer of gas without which we could not survive, the atmosphere. Other planets also have an atmosphere, basically nothing special. But the composition of the Earth's atmosphere is different from that of all other celestial bodies.
78% of the Earth's atmosphere consists of nitrogen, 21% of oxygen, and then there is a noble gas, which we call argon, of which there is 0.9%. That is already 99.9%. If that were all, we would share the fate of Mars. We would have an icy desert here, temperatures of around minus 18 degrees Celsius. Fortunately for us, there is this tiny little remnant containing greenhouse gases, and CO2 is one such greenhouse gas which ensures that part of the heat is trapped within the atmosphere and cannot escape into space. And this is why the Earth's surface is comfortably warm and why there is also life on planet Earth.
The natural greenhouse effect. Part of the sun's energy is retained on the Earth's surface and warms it. But solar radiation is not always constant. There are regular fluctuations and hence climatic changes. The reason for this is the position of the Earth.
There are Earth's so-called orbital parameters, that is, the Earth's orbit around the Sun, for example, which is not a constant. It changes every 100,000 years from an ellipse to a circle and then back to an ellipse again. But the axial tilt of the Earth, the orientation of its axis in space, also changes every 40,000 years like a wobbling, spinning top. And these are the three most prominent time scales we see in reconstructions: 100,000 years, 40,000 years, and 20,000 years.
The so-called Milankovitch cycles appeared in the past millions of years in the form of ice ages and interglacial periods. Information that reaches so far into the past comes mainly from drill cores. Ursula Röhl guards an enormous treasure trove of data. About 250,000 sediment cores are stored in the cold storage facility at the Center for Marine Environmental Sciences in Bremen, Germany. Strung together, it amounts to about 158 kilometers. At 4 degrees Celsius, the average temperature in the deep sea, drill cores from over 90 expeditions are stored. These provide rare insights into the history of the planet, if you know how to read them.
Drill cores are like a history book, where each page covers a different time period, recording particular events, and can reconstruct climate variations in the past, for example.
To procure the pages of this book, samples have been collected from all the world's oceans since the 1960s. A single drill core can map several thousand years of Earth's history. Microfossils and other components sink to the seabed and pile up on top of one another. And thus, about 1 centimeter of sediment is deposited in the deep sea over a period of 1,000 years. Every now and then, the researcher finds animal traces or evidence of prehistoric catastrophes.
So there are cores here that are very old. This one, for example, is very famous. This core contains the so-called Cretaceous-Paleogene boundary, which is related to the extinction of the dinosaurs. A brown fringe is particularly characteristic up here. And if you go in there with a chemical analysis, you find that this brown fringe has a high content of the chemical element iridium, which does not occur on Earth in this concentration.
This iridium anomaly points to an extraterrestrial origin in the rock layer, a meteorite impact 66 million years ago. The core halves also contain information about water temperature and CO2 content, important data about climate changes in the Earth's history.
Here, the cursor is now exactly at 56 million years, where an abrupt change occurred. That is, abruptly in the sense of within 1,000 or 10,000 years. And the amounts of carbon released then were of the same order of magnitude as they have been since the beginning of the Industrial Revolution. And that is essentially what is so worrying.
Worrying because a similar amount of carbon has been released in the space of just 200 years as was released in a few thousand years during the Paleocene epoch. Although the Earth's climate history is turbulent, the climate has been relatively stable for the last 10,000 years. Since about 1880, however, there has been a measurable increase in temperature. The changes are not the same everywhere. The global average is 1.1 degrees Celsius warmer today than it was before 1880. And 2011 to 2020 was the warmest decade since weather records began.
The sun provides more than 99.9% of the total energy coming to the Earth from outside. That's why it determines our climate system, meaning that if the sun were to undergo severe changes, the climate would also go haywire. But we must also bear in mind that the past 10,000 years is the time when human civilization just got started. When humans started to settle, working the land and so on, that was a time of a relatively stable climate. However, when looking at the past 100 to 150 years, we can say that the sun has only played a subordinate role. We have to look at ourselves and see that it's the changes we have brought about in the composition of the Earth's atmosphere that are critical here.
Temperature changes within just 200 years, much too fast for astronomical developments. These tend to influence the climate over several thousand years.
Yes, we often hear that it is completely normal for the climate to change. This is true, of course. There have been ice ages and warm spells. What we are experiencing now, however, is something on a completely different scale. The last ice age was 20,000 years ago. Then the climate changed to its current warm period within 10,000 years. And now we are producing such changes in the span of just 100 years. And that, of course, is something completely different, making it extremely difficult for ecosystems to adapt.
When external influences warm the Earth, chain reactions, or what we know as feedbacks, occur. A warmer Earth emits a greater number of greenhouse gases. More water vapor and CO2 enter the atmosphere, and the Earth heats up even more. Today, the external triggers from space are largely absent. Humans are directly responsible for amplifying the natural greenhouse effect and warming the planet.
There is the natural CO2 cycle or the natural carbon cycle, and atmospheres and oceans exchange huge amounts of CO2, for example. But overall, it is balanced. This means that the oceans lose as much as they gain from the atmosphere. And what humans do is they produce a disturbance through the emission of greenhouse gases, above all through the burning of fossil fuels, which throws the carbon cycle off balance, as evidenced by the level of CO2 which continues to rise.
While humans have long used carbon for energy, indeed the campfire is considered the cornerstone of human culture, these quantities were manageable. The hunger for energy has been growing for about 150 years. More and more stored carbon is burnt and enters the atmosphere as gas. Globalization, population growth, and digitalization are all consuming an increasing number of resources.
At the end of the day, it's about the time frames. If we humans were to release CO2 into the atmosphere over such long periods of time as coal or oil have developed, for example, it would have virtually no effect on the climate. But we are doing it in virtually the blink of an eye in Earth's history, and that is the problem. That we are releasing CO2 into the atmosphere at an incredible rate, and therefore cannot be reabsorbed in time or fast enough by the carbon sinks.
Many factors influence the climate. It's a complex interplay. Not all connections are directly recognizable. Others can even be observed from space. More than 50 years after the photo of the rising Earth was taken, space travel is playing a crucial role in protecting the only habitable planet in our solar system. Today, especially for monitoring the oceans, satellites are indispensable.
The sea is what makes planet Earth habitable for life as we know it. And that is because this large water surface, 70% of planet Earth, makes a fundamental contribution to good heat distribution. And the sea and the large water surface are also responsible for the fact that there's a water cycle, rain where it is needed, that nutrients are absorbed, processed, carbon is deposited. In the sea, as on land, plants work with the help of sunlight. They're able to split the water and thus produce oxygen as a waste product of photosynthesis. And you wouldn't believe it, because there are no trees in the ocean. So it's almost inconceivable that the ocean produces as much oxygen as the land, that we can say every second breath we take comes from the oceans. It is oxygen made by the oceans.
The Earth's polar regions are a particular focus of research. 2 satellites keep an eye on the Earth's ice surfaces. ESA's Cryosat-2 satellite and its American colleague IceSat-2 use radar and laser instruments to collect data on the state of the polar ice layers. Recognizing seasonal and long-term fluctuations is particularly important for climate research, because the Arctic is warming at least twice as fast as the rest of the world. In 2019, the surveying of ice surfaces got a very practical application. The Alfred Wegener Institute for Polar and Marine Research sent its icebreaker Polarstern on an Arctic expedition of unprecedented scale. With over 400 scientists on board, the ship set sail from Tromsø, Norway, heading north. The plan? Collect data on the central Arctic in winter. An ambitious undertaking, given that the central Arctic is covered by the impenetrable layer of ice throughout the winter. To take measurements there, you have to set out as early as autumn and let yourself be trapped by the ice masses. The expedition entitled Mosaic would probably not have been possible without the support from space.
When the Mosaic expedition was planned, it was clear that everything revolved around sea ice, because it was a question of predicting where we could go at all, how we would reach the Polarstern, how the ice would behave. Just finding out what the best ice flow is to explore for a year's research was a huge remote sensing task, because we wanted to find an ice flow that would last for a year.
In the Arctic winter, when the sun barely rises for months, the research station itself provides the only light there is. But the expedition members are not completely blind during polar nights. The eyes from space have the Polarstern firmly in their sights.
We had a great exchange during Mosaic, even with the crew of the ISS, the International Space Station, who called the ship. And in general, the Mosaic expedition, the one-year exploration of the North Pole, really felt a bit like a space mission.
The Arctic not only shows the effects of global warming on a unique ecosystem, but it also has a direct impact on the Earth's climate. The darker the surface of the Earth, the more incident solar radiation it absorbs, like a black t-shirt in the sun. If, on the other hand, the surface is bright, it reflects more light and has a cooling effect. This process is called ice albedo feedback. So, if the Earth's ice sheets melt, this further increases the warming, and even more ice disappears. The summer ice cover of the Arctic has already shrunk by a third since satellite measurements began in 1979.
When we compare the Arctic and the Antarctic, we discover that the Arctic is very different from the Antarctic. It's an ocean with land around it. And in the Antarctic, we have a continent with ice on it, 2 to 3 kilometers of ice. So when we measure Antarctic temperatures, we are 2 to 3 kilometers higher than in the Arctic. The Arctic is also surrounded by land masses that warm up more quickly, and so it warms up much faster than the other regions we know. The Mosaic expedition showed that in Fridtjof Nansen's time, when he first did such a drift expedition, the winter was 10 degrees Celsius colder on average than it is today, a difference that is terrifying. A 10-degree difference is crazy. And during the Mosaic expedition, the researchers sometimes observed that within a few days, the temperatures jump by 40 degrees Celsius. So from around minus 30 degrees to plus degrees and back again. And this dynamic, it's new. It doesn't belong there.
The rest of the oceans also influence the Earth's climate system. The water absorbs heat from the atmosphere and cools it down. With the help of the polar regions and ocean currents, the warmer waters redistributed globally. The seawater also absorbs CO2 directly and distributes it down to the depths. In addition, animals, plants, and single-celled organisms in the ocean bind CO2 and process it into biomass. For example, the oceans have absorbed about 30% of human CO2 emissions. They act as a climate buffer, an important contribution against global warming. But for how much longer? The warmer the water in the oceans, the less CO2 it absorbs. At the same time, warming threatens marine life.
The whole thing is both a curse and a blessing. Marine ecosystems are stressed by warming alone. Tropical corals in particular are suffering, as we can already see today with the increase in so-called coral bleaching. But then there is also the acidification of the oceans due to CO2 absorption, because the CO2 reacts in the water to form carbonic acid. And everyone knows that this cannot be good for marine organisms, especially not for those that have to build up calcium carbonate structures.
This can have an impact on the whole food chain, all the way to humans. If the oceans warm up, this also has an effect on sea levels. Warm water has more volume than cold water and expands when heated. The level rises. In addition, there is meltwater that previously lay in ice sheets on land. The changes in water and ice surfaces also have an impact on a barely visible field of research, the Earth's gravity.
2, 1, and liftoff of Grace follow-on.
The Grace satellite mission of NASA and the GFC, German Research Center for Geoscience in Potsdam, is investigating the planet's gravitational field. In 2018, the second satellite generation, Grace Follow-On, was launched. The revolutionary idea? Changes in the Earth's gravity indicate mass shifts at the Earth's surface, because not every area on Earth has the same gravitational pull. Basically, the greater the mass of an object, the greater its gravitational pull. Thus, a mountain range has a higher gravitational pull than a lowland plain, and water movements or changes in the ice sheets also influence gravity.
The total mass of the Earth remains constant in the very first approximation. The solid Earth plus the oceans plus the atmosphere above it, all that remains the same. But practically, there's a huge cycle in this system. Take the water cycle, for example. When water warms up over the oceans, it evaporates into clouds, which rain down somewhere. And then we can see on our maps at which point, in which month, which mass was located where.
For these measurements, the two Grace satellites fly behind each other at an altitude of 500 kilometers in polar orbits. They are 220 kilometers apart and continuously measure their distance from each other. Depending on the gravitational pull between them, the distance between the twin satellites changes.
You have to imagine that when the two satellites fly from the south towards India, they first fly over the Indian Ocean, which means the gravity over the Indian Ocean is still relatively uniform. Then they fly over the Indian lowlands and at some point reach the Himalayas. The Himalayas, due to their somewhat larger mass, have a stronger effect on the first satellite reaching the Himalayas, which means it's attracted by this mass. And the satellite flying 220 kilometers behind does not yet notice this so clearly. Therefore, the distance will definitely increase. And this works like an accordion, so to speak. Such an accordion effect, which we continuously measure 10 times every second, will be collected to calculate the gravitational field globally.
The distance between the satellites is measured using microwaves, and on the new Grace Follow-On mission, laser-ranging interferometers. The smallest deviations are registered, a complicated undertaking because interference factors must always be taken into account.
When the two satellites fly around the rotating Earth, the distance between the two satellites already changes by 2 kilometers every orbit. But what interests us are the mass distributions. And one of the largest signals that you get from the Earth is, for example, the Himalayan mountains. And you can calculate that this signal practically accounts for about 100 micrometers in the change of distance.
100 micrometers, about the thickness of a sheet of paper. In order to distinguish these minimal gravitational signals from interference, the Grace Follow-On also has GPS sensors on board, as well as accelerometers to determine the overflight altitude or detect braking effects. What remains are the smallest changes in gravity. The Potsdam gravity potato of the GFC is an exaggerated representation of the Earth's gravitational field deviations. Most of the Earth's gravitational pull comes from the mass inside the Earth. A tiny fraction, however, is due to the water on or near the surface. Oceans, rivers, lakes, glaciers, and groundwater change much faster than the viscous rock inside the Earth. Regular measurements can detect these movements, especially for the changes in the ice masses. Recording from space offers unique possibilities.
With GRACE and GRACE
Follow-On, we've now made observations for 20 years. And we can show, for example, that in Greenland, since 2002, an average of about 270 gigatons have practically disappeared every year, melting into the oceans and contributing to the sea level. A gigaton is a cube of ice with a side length of 1 kilometer. So that, accumulated over 20 years, leads to approximately 5,000 such ice cubes. So there are dramatic processes going on.
Sind also dramatische Vorgänge im Gange.
In the past decades, sea levels rose by 3.3 to 3.6 millimeters every year, an average value. Due to tectonic movements, local characteristics, and currents, water levels can vary regionally. On some coasts, the water rises 4 times as much. On others, it even sinks. In total, the sea level today is more than 70 millimeters higher than it was in 1992. In order to detect dangers to human settlements early enough, area-wide monitoring is needed. The most extensive Earth observation program is currently run by the European Commission, together with the space agency ESA. The Copernicus program is designed to observe the Earth and